Good morning, everyone. Welcome to the Toronto Geometry Colloquium. This is a weekly web series all about geometry processing. This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities.
Every week, we will have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation.
And today, it's my pleasure to present two great speakers working on geometric deep learning. We have Lior Yariv as our opener to talk about multi-view neural surface reconstruction, and Rana Hanocka as our headliner to discuss deep learning on single shapes. And if there are any questions during the talks, please leave comments in the YouTube live chat. And our opener, Lior, is a computer science master's student at Weizmann Institute of Science, supervised by Yaron Liebman. Her research focuses on the red hot topics, geometric deep learning, and especially she was working on a lot of fundamental problems about how can we represent shapes using a level set of a neural net. And recently, she also showed that this representation, called neural implicit, could be a very powerful tool to recover geometry, material, and camera parameters from images. And this work has recently been accepted to NURBS as a spotlight paper. So without further ado, let's welcome Lior to talk about the neural implicit, a differentiable renderer.
Thank you. 1 second, let me share my screen. Wait. Okay, can you see my screen? Okay, I hope you see it. So thank you for the nice introduction. So I'm Lior, as presented, from the Weizmann Institute of Science, and I will present to you our recent work on multi-view neural surface reconstruction. So in this work, we want to address the challenging problem of multi-view 3D surface reconstruction. When that is given 2D images capturing a real object from multiple views, our goal is to infer the three unknowns of the scene. That is the 3D geometry of the object, which we would like to represent as a surface. Its appearance consists of the surface properties and lighting in the scene, and the camera location and orientation which capture those images. For that, we present implicit differentiable render, a neural network architecture that simultaneously learns those three unknowns. IDR able to produce high-fidelity 3D surface reconstruction by disentangling geometry and appearance, learned solely from mass 2D images and rough camera estimates. A recent successful neural network approach to solving this problem is by feeding those three unknowns into differentiable rendering system. That is, simulate the rendering of the scene from a given view and comparing the rendered image to the original image. The key challenge is how to make the render a function of the geometry that is independent of the object material or the scene lighting. Differential rendering systems are mostly based on raycasting or rasterization, while popular models to represent 3D geometry include triangular meshes, volumetric grids, and also implicit neural representation. In a recent work by Neymer et al., they introduced such differential render model that can represent arbitrary texture, but it cannot handle reflectance and lighting effects, nor can it handle noisy cameras. Concurrently to our work, NERF by Midenhall et al. Used neural rendering for novel view synthesis from a set of images with known cameras, where differently from IDR, the method doesn't produce a surface reconstruction of the scene geometry rather than a three-dimensional density field. In our work, IDR, we reconstruct an implicit surface together with a surface light field that is separated from the geometry, and we can handle both exact and noisy camera information. So, as I said, our geometry is represented as the zero level set of a fully connected neural network F, which models for each 3D point its sign distance function to the shape, as you can see in the example here from the right. Now, given some learnable camera position C and some fixed image pixel P, we would like to produce the color of the pixel as a differentiable function of the geometry, appearance, and camera. The camera orientation and pixel define a viewing ray, V. And we can trace for the first intersection of the viewing ray with the implicit surface, denoted by X. We denote the distance to the camera as T and N to be the corresponding surface normal. Now, the first step we want to do is to represent this intersection point X and its normal n as a differential function of the implicit geometry and the camera parameters. We implement it by simply composing the neural network with a fixed linear computation at the entrance and another at the outputs. The idea behind this derivation is that it incorporates correct derivatives with respect to the geometry and the camera parameters C and V. Secondly, we want to approximate the color of the pixel P, determined by the radiance reflected from the surface to the camera. Our interest is that the renderer will not memorize any part of the geometry or the viewing cameras. Therefore, we suggest representing the light field as a function of the surface position, surface normal, and viewing direction. This is implemented using a second neural network M, taking as input X and V, and output RGB values. Incorporating the normal and the viewing direction is necessary for 3D reconstruction that is decoupled from the appearance and the cameras. And I want to explain this fact using really simple examples. If we take in a renderer without normal information, it will produce the same light estimation in those two cases. Therefore, can result in a renderer that can compensate over geometry properties, while a renderer without viewing direction will produce the same light estimation in those two cases, where in real life, the scene appearance is likely to be view dependent, for example, to model specularity. To complete our IDR model, we introduced a global feature vector of the geometry, which allows the renderer to reason about global lighting or shading effects. Then we compare our final radiance approximation to the ground truth pixel color to simultaneously train the model's parameters. And of course, we can optimize it across multiple pixels and images. Additionally, inspired by NERF, we add positional encoding to the 3D position entering the implicit network F and to the viewing direction entering the renderer. This nonlinear embedding improves the learning of high frequencies and enables our model to faster converge to the highly detailed results. We apply our multi-view surface reconstruction model to real 2D images from the DTU dataset. This dataset consists of various scans, each include either 49 or 64 high-resolution images of objects with a wide variety of materials and different shapes. Here we show the reconstructed geometry, i.e. the zero level set of the neural network F, and the rendering of novel views gained from the neural renderer M, when using fixed ground truth cameras. Now, towards the goal of disentangling this geometry and appearance property, we show that we are able to transfer the appearance learned from one scene to different unseen geometry by simply switch between the rendering networks for two pre-trained models. Note that without using the normal in the renderer, the geometry is not well approximated. And the renderer fails to produce plausible rendering of different geometries, although the light field approximation is showing in the rendering column looks reasonable. We compare our results with the popular non-deep learning approach COMAP and to the related work DVR, where you can see how the shapes artifacts may occur due to lighting or specularity effects. Here we show results in the setup of trainable cameras with noisy initializations. We show our surface reconstruction compared to COMAP SFM, and we further show results of IDR training with fixed cameras set to the inaccurate camera initialization. This indicates that the optimization of camera parameters together with the 3D reconstruction is indeed significant. And here are some more results for the trained camera setups. And you can appreciate and see how our model is able to produce state-of-the-art 3D reconstruction with high fidelity and details, as well as realistic rendering for novel views. So to conclude, I introduced to you IDR, which is an end-to-end architecture that handles unknown geometry, appearance, and cameras, and can disentangle between the geometry and the appearance of the scene. Moreover, it is the first step method that expresses the dependence of neural implicit surface on camera parameters. However, one limitation of IDR is that it requires a reasonable camera initialization, and it cannot work with, for example, with the random camera initializations. An interesting future work that we are thinking about it is to combine an IDR with a neural network that will predict camera information directly from the images. Another thing is that IDR is learned per scene, and we think there is an option to leverage this model to learn from a large data set in order to inference new scene reconstruction much faster. Another very interesting future direction is to further factor the surface light field into surface materials properties and lighting in the scene. For more details, you're more than welcome to take a look at our project page, and we have just released our coding data and it's available there. Really, thank you for listening and thank you for having me here.
Thank you, Lior, for the great talk and the great set of slides. So, here we have a quick question for you. So your render is based on like the implicit representation of the shape, but there are also a lot of differentiable render like based on the mesh representation of the shape, like combining with the multi-call sampling. And my question is what is the pros and cons comparing these two types of differentiable renderers?
So first is the big benefits of implicit neural representation, also that comes from the expressive power of the neural network, and also it's not really fixed discretization like that can occur sometimes with mesh, or even there's like a representation of implicit surface over volumetric grids. And yes. I hope it did answer your question.
Yeah. Okay, that's good. Okay, thank you for the answer. And due to the time, let's proceed to the talk of our headliner, and we will have another joint Q&A session at the end of the presentation. And so our headliner, Rana, is a PhD student at Tel Aviv University, and she's co-supervised by Daniel Conor and Raja Giris. And she's also an expert in geometric deep learning, but she focused more on developing machine learning models for triangle meshes. So perhaps the most representative example is the mesh convolutional neural net presented at last year's SIGGRAPH. And since then, her papers basically continue to surprise us with the capability of deep learning on solving classic geometry problems. And typically, we may think that using machine learning approaches will require a lot of training data, but today, she's going to talk about something very counterintuitive. She's going to show that how can we train such a machine learning model with only a single training shape. So now please join me to welcome Rana to tell us what is this magical trick.
Thanks, Derek. Thank you for the very nice introduction. Can you see my screen? Yeah, great. Okay. Yeah, so I just want to start off by thanking the organizers, Derek, Sylvia, Xiangwei, and Alec for putting this all together. So thank you for that. Okay, so let's get started. Right now, we're in a really exciting time where we're witnessing some amazing advances in deep learning, and in particular, there's been some fantastic progress on images and videos. But 3D deep learning is still pretty young and developing. And one of the reasons for that is that there are still fundamental and open questions in deep learning on geometry that have yet to be answered. So for example, there isn't a universal approach for applying deep neural networks on shapes. And one of the reasons for that is that we don't really have a good answer for a universal way to represent shapes. We just heard about implicit functions from Lior, but there's also point clouds, volumetric approaches, 2D projections, graphs, and meshes. And each one has its own pros and cons. One of the most popular representations in computer graphics is the mesh representation, and it has unique advantages like being efficient and it accurately portrays the shape structure. But this representation is irregular and unordered, which makes the definition of convolution, for example, ill-defined. A mesh is an unordered list of XYZ coordinates in space, as well as an unordered list of triangles or connectivity between each vertex. So in one of our earlier works, Mesh CNN, we proposed a technique for applying neural networks on the irregular mesh structure. Every vertex in a mesh can have an arbitrary number of neighbors, and there's no order between them. But a nice property of edges in manifold triangular meshes is that every edge is adjacent to exactly 2 triangles, which gives a nice fixed size neighborhood of 4 edges. So every edge in the mesh has an n-dimensional feature vector associated with it, and we learn convolutional filter weights, which are applied on each edge feature vector and the 4 neighboring edge feature vectors. We also proposed a pooling operation which reduces the resolution of the input mesh through an edge collapse operation. This forces the network to reduce and strengthen the learned representation. And the input mesh resolution can be restored via an unpooling operation. So for more details, check out our paper. But still, even though this is just one take on many different takes on how to build deep networks for 3D shapes, there's still more challenges. And one is that we don't really have in geometry large and clean data sets. And so I want to back that up a bit at first by saying that this isn't the entire story. On the one hand, we do have a lot of geometry in the wild, which comes from a variety of different sources, but this data isn't really clean. And it's difficult for us geometers to work with. And if you're curious about why robustly handling geometry in the wild is difficult, you can just ask Alec. On the other hand, there are some clean data sets, meaning they're manifold, watertight, etc. But these are very small. So far during my PhD, we've explored some challenging problems in geometry, including registration, synthesis, reconstruction, point cloud consolidation, which all require learning some type of prior. Some of these works focused on learning from large collections of shapes. So in the case of a line net, this was possible because we voxelized the meshes and learned a warp field that we applied on the original high resolution mesh, which kind of avoided the need to work on meshes directly or have a large clean mesh dataset. And in Point GMM, we presented a new way to represent shapes using a hierarchical GMM representation. But today, I'm going to be focusing on a couple works that learn from single shapes. Specifically, I want to talk about how we can leverage the representational power of deep neural networks on different problems in geometry processing, which rely on only a single given input shape. I'm really excited about this direction because it opens the doors for a lot of different possibilities when we don't have to rely on large, clean data sets. And in this talk, I'm going to focus on 2 recent works and briefly touch on a work in progress, which all learn from a single shape. So to start off, I'm going to dive into a work we recently presented at this year's SIGGRAPH called Point2 Mesh, which uses deep learning for the problem of surface reconstruction. So reconstructing a surface mesh from an input point cloud is a long-standing problem in computer graphics and computer vision. In this work, the idea is to reconstruct a watertight mesh from an input point cloud where the convolutional neural network defines the prior. Instead of explicitly having to specify the prior or handcrafting it, it's learned on the fly from the single input point cloud without any pre-training. Surface reconstruction has been studied extensively for 20 years, and the key challenge is that the problem is ill-posed. This means that there's many valid solutions. So consider these 4 points sampled from a 2D curve. You can imagine that there are infinitely many solutions that pass through these 4 points. So in order to pick a favorable solution, we should design some type of prior which captures the expected shape properties. But building a prior is challenging, and reducing what we know or can expect into a simple prior often oversimplifies the problem and can't really encapsulate the wide range of possible scenarios. On the other hand, we also want to avoid the need to handcraft a specific prior for every single scenario. This often results in having to define some type of generic smoothness prior. And even though shapes are typically piecewise smooth, this generic prior isn't specific enough to the current input or tailored enough to the current input, which can result in overfitting to noise. For example, observe the noisy bumps around the tail region. In Point2 Mesh, we introduced the idea of a self-prior, where the prior is learned on the fly from the input point cloud itself. And you can already see that the ridges on the dinosaur back are faithfully reconstructed while still removing noise and outliers. So from a high level, we start with an input point cloud and an initial deformable mesh, and then a CNN iteratively deforms the mesh to shrink wrap the input point cloud. Specifically, the CNN weights are optimized to displace the vertices of the initial mesh such that it best fits the input point cloud. This ensures that the reconstruction is watertight, which is a desirable property since real objects are solid. And this is especially important for surface reconstruction since the input may contain holes or regions with low density samples. We said we optimized the CNN weights to displace the vertices of the mesh, but why not just displace the mesh vertices directly? Well, as we said before, there are many valid solutions, and as it turns out, a direct optimization leads to an undesirable result. But if we optimize the CNN weights instead, their inductive bias acts as a powerful prior, which leads to favorable solutions. This approach learns from a single input point cloud, and the premise is that shapes are not random. They contain strong self-correlations across multiple scales. The optimized CNN weights act as a prior, which is what we call the self-prior. And this self-prior encodes the expected shape properties and leverages the natural repetitions that are present within a single shape. Central to the self-prior is the global weight sharing structure of a CNN. So on the one hand, convolutions are applied locally to extract salient features, and on the other, the same local kernels are optimized over the entire shape. Optimizing kernel weights globally across the entire shape inherently encourages local scale geometric self-repetition across the shape, the reconstructed shape surface. So we leverage the inductive bias of neural networks to learn a self-prior for surface reconstruction. This self-prior is powerful in completing missing parts and removing outliers or noise. For example, reconstructing a mesh from a point cloud using a smooth prior ignores the character of the global shape, whereas the self-prior learns a more plausible reconstruction. So here's the gist of our approach. We start with some input point cloud, and we use this to calculate an initial mesh. If we know the genus is 0, we can compute the initial mesh using the convex hull. For non-zero genus shapes, we can use some other techniques, and I'll talk about that a little bit later. The initial mesh is used as an input to a CNN, which predicts the vertex displacements and applies them to the initial mesh. This initial mesh is used as input to a CNN. Sorry. The deformed mesh is then passed to a differential sampler, and then this results in a sampled mesh. We calculate the distance between the sampled mesh and the input point cloud, which is used to update the CNN weights. And then we iteratively perform this update where the deformed mesh in the next iteration should more closely approximate the input point cloud. The CNN used in this work relies on the earlier work that I mentioned, mesh CNN. So traditionally, the inverse problem formulation defines the optimal reconstructed mesh, M star, by minimizing an objective function. This contains an energy term, E, which tells us how good the reconstructed mesh, M hat, fits the input point cloud X. But remember, there are many reconstructed meshes which satisfy this condition, so a regularization term R is introduced. Traditionally, this is a handcrafted term, which encourages smoothness. In this work, we want the network to automatically define the prior for us, and this idea was first presented for images in deep image prior. Here, we say that the optimal reconstructed mesh, M star, is some parameterization of a neural network F with weights theta, using a fixed random tensor C as input. So instead of optimizing for the best reconstructed mesh, we optimize for the best network weights, theta star, such that our energy term is minimized. And note that the network has a limited capacity, so it can't reconstruct every possible mesh. In particular, a fixed set of local kernels are optimized to displace the vertices over the entire shape, which forces the network to infer global shape statistics and implicitly prevents overfitting. This unique structure defines a prior that leverages the representational power of neural networks to favor good solutions. So actually, in deep image prior, the authors reported a tendency for the network to overfit to the noisy input, which was prevented using early stopping. And in this work, we didn't observe the same phenomena, which we think in part can be explained by the fact that the mesh structure itself also acts as some type of prior. In particular, the triangles of a mesh are piecewise smooth, which means they naturally iron out noise. The initial deformable mesh, M, defines the adjacency information for the convolutions and pooling in mesh CNN. However, unlike mesh CNN, here our input features are a fixed random feature tensor per edge, C. Since mesh CNN operates on edges, the network abstracts each random feature tensor in C to a displacement vector per edge. But we want to displace the vertices of the mesh, so for every single vertex, we average the edge displacements over all of the incident edges, resulting in a displacement vector per vertex. This displacement is added to the vertices of the initial mesh, which results in the current estimate of the reconstructed mesh. And these displacements are differentials. So we initialize the weights to give 0 in the first pass. And then, in that first pass, we'll have a reconstructed mesh that looks like the initial mesh. This reconstructed mesh goes through a differential sampler. First, the sampler randomly selects a triangle with probability proportional to the face area. And then a point is randomly sampled on the triangle surface whose XYZ location is defined by the 3 triangle vertices, which is how gradients are backpropagated through the sampler to update the CNN weights, which ultimately displace the vertices. So the loss is computed by comparing the sampled reconstructed mesh to the input point cloud. And specifically, we use the bidirectional chamfer distance, which means for every single point in the reconstructed mesh, we take the closest point in the input point cloud and we sum them. And the same thing for the other direction. So we sum all the distances from the input point cloud and find the closest point in the reconstructed mesh. And in addition to this Euclidean distance, we also compare the normals between the input point cloud and the reconstructed mesh. In practice, we employ this framework in a coarse-to-fine manner. So what that means is we'll start with a coarse or a low resolution version of the initial mesh, which is roughly a few thousand faces. And then we run 1,000 iterations of this procedure. We pass the reconstructed mesh to a robust watertight manifold technique. This increases the resolution and it smooths the result. And then we initialize a new network. We discard the old network weights and we have a new random feature tensor as input for this higher resolution mesh. And we rerun this optimization procedure again, usually for 1,000 iterations. And we repeat this process until the desired resolution is obtained. So now I want to highlight to you why the network really acts like a prior. So in this example, I think you can see that well. So consider this input point cloud and corresponding initial mesh. When we optimize the CNN weights, the mesh enters this difficult second order cavity. But if we optimize the mesh vertices directly using the same exact objective, you can see that it becomes trapped in a local minima. And so I think this example is really powerful because it shows us that the CNN weights, they act like a prior, and by encouraging self-similarity, we can avoid poor local minima. So another example of how the convergence looks, you can see there's some low density sampled regions, and we're still able to accurately reconstruct those regions. And here's a few more examples of that, as well as an example with some details. So we also used a real 3D scanner to scan these toys pictured above here. It's difficult to see, but there are actually some pretty significant regions on these objects that the scanner failed to accurately sample. And our reconstruction is still able to produce a nice result in those regions. We also compared against existing techniques on the tasks, for example, of denoising. The most popular method for surface reconstruction is Poisson reconstruction, which uses some type of smoothness prior. And in this case, it overfits to noise. Another work I want to discuss is the deep geometric prior, DGP. So this also learns reconstruction from a single shape, but there's two main differences compared to our technique. So the first main difference is that it optimizes local patches to the input point cloud. So it does not produce a watertight surface. And the second main difference is that each local patch is optimized separately without any global shared weights. So there's no information shared between different patches. And so with our self-prior, we can see that this global weight sharing enables removing noise. So we also compared it against the same techniques for the task of handling missing parts. So existing techniques do not utilize any genus information. So they can introduce topological errors and reconstruct a surface with the incorrect genus, for example. And without global weight sharing over a single watertight surface, it might be difficult to properly fill holes. And since the genus is provided implicitly to our method via the initial mesh, this provides control and it can be seen as an advantage for hole filling. So I mentioned before, we can provide a non-zero genus input to our method. And here's an example of that. So in this example, Poisson reconstructs a surface with incorrect topological holes. And we can apply a low resolution octree to close these incorrect topological holes. And this creates a coarse mesh, which is used as the initial mesh in our technique. And the result is a topologically correct mesh, which preserves the details from the input point cloud and does not overfit to incorrect low density regions. So using a coarse mesh, coarse resolution octree on the result of Poisson, for example, Poisson reconstruction is another way of estimating the initial meshes with unknown genus. So the recap of this work is that we propose a method for surface reconstruction, which learns a prior on the fly from the input point cloud. This self-prior is effective at removing noise and outliers. And the key is the global weight sharing, which implicitly favors good solutions. Some important takeaways are that it is possible to learn from a single shape and that shapes are not random. They contain strong self-correlations, which are exploited by the self-prior, or in other words, the self-prior learns the shape. So the next work I want to talk about deals with synthesizing geometric textures, and this was a work that we also presented in this past SIGGRAPH. The idea is we're given a 3D exemplar which contains some geometric texture, and we would like to train a neural network that can automatically understand and then synthesize the exemplar's geometric texture. So when given a different target shape, we could synthesize the geometric textures from the exemplar over the target shape. If we had a 2D displacement map, we could compute a parametrization of the 3D target surface onto the plane, and the resulting textured model can be used to displace the vertices of the target shape in the, for example, normal direction, which would result in a 3D texture. But we don't have a 2D displacement map. Instead, we're given a 3D exemplar model, which has geometric textures ingrained in it. It's not represented as a 2D parametrization over our base shape, and it's not entirely clear how we could disentangle a 3D geometry into some base and 2D displacement map. So in other words, the geometric texture is not provided explicitly and the statistics are unknown, yet we would still like to be able to automatically learn how to synthesize the unknown 3D geometric structures from the exemplar over arbitrary target shapes. And in particular, geometric textures can't always be represented as a simple displacement over a base shape. For example, a 2D displacement map that moves geometry in the normal direction is limited since it doesn't encode tangential movement. So synthesizing geometric textures over some target shape involves building geometric structures progressively by iteratively displacing vertices in all directions. For these reasons, we want to develop a technique that analyzes and then can synthesize the geometric structures directly in 3D without parametrization of the exemplar or the target shape. So we want to progressively build the geometric texture by iteratively adding incremental 3D displacements to some base shape. And this involves iteratively displacing the vertices of the base shape and then increasing the resolution of the displaced result. The idea is to learn to synthesize the unknown geometric structures over the base shape in such a way that later it can be synthesized on arbitrary, unseen target shapes. And specifically, these target shapes might have different triangulations or genus than the training shape. And the base shape can be obtained for generic shapes via mesh simplification, which gives us some type of coarse approximation of the exemplar. So like in our previous work and like all the works on this talk, we want to train a deep neural network to learn the geometric textures from a single exemplar. And this seems tricky, right? Because we don't have a large collection of shapes which all contain the same geometric texture. But there is actually a lot of self-repetitions in textures where local neighborhoods contain similar statistics. So the objective is to learn the unknown texture statistics from local triangular patches. Starting with a base mesh, we learn deep features on the faces of the input triangulation, and this is used to generate vertex displacements. This output is upsampled, or in other words, subdivided before going to the next level generator, which displaces the vertices. And this process is repeated until reaching the finest level in the series. This slide is important because it presents the general gist of our approach. We train a series of generators which progressively add geometric detail to an evolving mesh. So our approach can be split into 3 phases. in the first phase, we create multi-scale training data from the 3D exemplar offline. In the second phase, we use the multi-scaled inputs as supervision to train a series of progressive generators. And then once we finish training, we apply the series of multi-scale generators to unseen target shapes to synthesize geometric textures. So we want to train this series of progressive generators, but how can we supervise each level? Specifically, we want to supervise the generators such that there's a ground truth corresponding mesh for every single level. So the progressively subdivided base shape needs vertex corresponding ground truth meshes for supervision, but how do we obtain these? We especially need to consider exactly how to subdivide the mesh, right? So it's compatible for both training and test shapes. Intuitively, we could think about creating multi-scaled training meshes by performing mesh simplification on the exemplar, which would be carried out via an edge collapse operation. But remember, the idea is to upsample the coarse mesh and learn to synthesize the geometric textures using the vertex corresponding supervised meshes. So in this case, the only way to restore the exemplar triangulation from the coarse mesh would be to memorize which edges were collapsed and in what order, and then reverse them. But this strategy, it would only work on the training mesh, right? Because the order of edge collapses on one mesh doesn't translate to different meshes. So in other words, we need compatibility between the upsampling operation that we apply on the exemplar shape and any arbitrary target shape. So for this reason, we decide to use a generic midpoint subdivision operation, which upsamples every mesh in the same manner by splitting each triangle into 4 triangles. But simply subdividing the base shape using midpoint subdivision will not produce the same connectivity as the exemplar. So for this reason, we remesh the exemplar such that this new triangulation is defined by a series of midpoint subdivisions over the base shape. Specifically, we create a series of progressive geometric textures via an offline optimization procedure. These shapes will be used as supervision to train the series of progressive generators. So to obtain the supervised mesh for the first scale, we minimize the distance from the base mesh to the exemplar by displacing the vertices of the base mesh. This optimization objective is measured by a bidirectional transfer distance between uniformly sampled points on both the exemplar and the optimized displaced mesh. To create the supervised mesh for the next scale, we first apply the midpoint subdivision operator, which is the same operator used by the network. And then we minimize the distance to the exemplar by displacing the vertices of the subdivided mesh from the previous scale. So this procedure is repeated until we obtain the desired number of texture scales. After this optimization is complete, we have a series of progressive texture meshes with the proper midpoint subdivision connectivity. And these meshes are what we're going to use to train the series of progressive generators, since they provide vertex level correspondence for the loss computation. Note, this offline optimization procedure is only necessary for training on the exemplar shape. During inference, we use the trained generators and fixed midpoint subdivision on target shapes with arbitrary triangulations. So similar to the fixed size neighborhood that we exploited for edges on Mesh CNN, triangles also have this nice fixed size neighborhood, since every single triangle in a manifold triangular mesh is adjacent to exactly 3 faces. So in this setting, we learn deep features on each triangle by learning convolutional kernels, which are applied on each face and the 3 neighboring faces. And this deep embedding is the building block for the generator and the discriminator networks. So the generator predicts a displacement vector per face, which is averaged over all the vertices that are incident to it. And this results in a displacement vector per vertex. The input to both the discriminator and the generator networks is a geometric feature that we extract to describe the local geometry. We build a local coordinate system based on the direction of the edge and the face normal. And then we use that to extract a four-dimensional feature vector, the edge length, what's shown here in pink, and the Cartesian coordinate of the opposite vertex to that pink edge, also shown in pink, in this local coordinate system. So we progressively train a series of multi-scale generators. This idea was first presented in SIGGRAPH for images, and we adopt their formulation here for 3D meshes with a few small twists. So in the coarsest resolution, we start with the base shape and we add noise to the vertex positions. Then the generator displaces the noised input, resulting in the fake output in the first level. The network is trained through, the generator network is trained through two losses. So the first is an adversarial loss from the discriminator, and the second is a reconstruction loss between the vertex corresponding vertices in the output and the ground truth. So after we finish training in this level, we upsample the output using midpoint subdivision. And then the generator weights in this previous level are frozen, and then we train the next level where the input is the output of the previous level. And we continue this process until the desired level is reached. So we train a series of generators on the following exemplar inputs. The texture is added progressively to the target shape. So starting with the coarsest level, the target shape passes through each generator, is subdivided, then goes to the next generator, and so on and so forth. And so this texture is built progressively. And here's another example of that. So our progressive training allows synthesizing meshes starting from different levels of the generator. If we start in the lowest level, which means using the base shape plus noise, the generator is going to output meshes with different global structures. Since it works on patches, it doesn't really consider any global information. So it can put the legs of the sheep on the head, things like that. However, if we're going to synthesize textures starting from higher levels, from coarser meshes, then the generator preserves the global structure of the input and will only deform and synthesize textures on local regions of the mesh. So the generators are not the only thing that control the scale space, the texture scale space. If we train on this spiky ball here, then we synthesize the textures over the torus. If we decrease the resolution of this target torus, the synthesized geometric structures will also change. They'll have a coarser scale space. And this is because the input triangulation defines the size of the scale space. It defines the receptive field for the convolutional kernels. So by sampling different noise vectors as input, we can synthesize slight variations of the same texture on the target shape. We can also interpolate between different variations of the synthesized textures, which results in this cool animation. So here we trained on an exemplar with complex 3D displacements in all directions. So the cross-section of the exemplar helps to illustrate that these repeating structures are built progressively by iteratively moving vertices in all directions. They can't simply be represented by displacement in the normal direction, for example. So you can see that the network learns to synthesize these complex geometric textures from the exemplar over arbitrary target shapes. And here's another example of that. So this framework is genus agnostic, meaning we can train on an exemplar with one genus and synthesize it over a target shape with a different genus. And this is possible since we only consider local patch statistics, which are very similar, even if the genus is different, right? In this case, we trained on genus 2 and transferred it to the fertility statue with genus 4. So in summary, in this work, we demonstrated that we could learn to synthesize the unknown 3D textures from a single exemplar shape. We train a series of progressive generators which displace the vertices in all direction, and it's agnostic to genus. So in the time we have left, I'm going to give a short teaser of a work in progress. We have an early snapshot in the archive, and if you're interested in reading more, you can check that out. So this is a work done led by Gal Metzer. So point clouds are acquired from scanners, and they are a noise and sparse sampling of the underlying 3D surface. And they often contain outliers or missing regions, as we saw in Point2 Mesh, right? But a lot of downstream applications, especially in robust graphics pipelines, demand that these point sets are perfect. And what that means is they uniformly sample the surface, they sample sharp features, they have oriented normals, all while being noise and outlier free. And so for these reasons, we want to use a point cloud consolidation process, which means we add points on sharp features and inside sparsely sampled regions, as well as removing noise and outliers. And here's a few teaser results of our method. So in this work, we build on some of the concepts that I showed you in our previous works. We perform point cloud consolidation from only the input giving point cloud. And we do this by repeatedly self-sampling the input point cloud with global subsets that are used to train a deep neural network. So the idea is that we define some source and target subsets according to some desired consolidation criteria. For example, if we want to generate points in sharp regions or within sparse regions. And then the network will learn a mapping from source subsets to target subsets. And this implicitly learns to consolidate the point cloud and generate the desired with the characteristic of the desired consolidation criteria. So we leverage the inductive bias again here of neural networks to eliminate noise and outliers, which is a notoriously difficult problem in point cloud consolidation. And the shared weights of the neural network are optimized over the entire shape, which learns some interesting non-local statistics. So we loosely partition these points of the input point cloud into two groups. And this is our rough approximation of the desired consolidation criteria. So for example, in the case of sharp feature consolidation, you can see a few examples of how points are roughly partitioned into sharp, which is red here, and not sharp, which is blue. And we use an approximate definition of sharp, which is basically we estimate the curvature of the points and we compare these, we estimate the normals of the points and we compare the normals. So it's basically an estimated curvature criteria. And even though this is not a perfect definition of sharpness, it's good enough because networks are good at regressing to the mean and understanding the core modes of the data. And we have like a similar rough definition of determining which points are in sparse regions. So during training, we repeatedly sample global subsets from the single input point cloud, where we rebalance the target subset to contain more what we call positive, or in this illustration, it's sharp points than their presence in the input point cloud. So on the other hand, the source subset contains a lower percentage of those points, of positive points, of sharp points. And then we train the network to repeatedly displace source subsets to resemble target subsets. And our loss is, again, the bidirectional transfer distance between these 2 point sets. During inference, we sample random subsets, global subsets, from the input, and these are repeatedly passed through the trained network G, which produces different consolidated subsets, and these are aggregated together to produce a final result at arbitrary resolution. So this process can be repeated as many times as desired, and each time we get a new point set with an emphasis on the desired consolidation criteria. So either points in sharp regions, for example, or in sparsely sampled regions. And one thing that we think is really interesting about this approach compared to like existing techniques that do deep upsampling, for example, is that we work on global subsets. And so we're able to exploit some non-local information this way. For example, if we take this input point cloud that was scanned with a 3D LiDAR scanner, it contains an undesirable sampling pattern. And if we train a network on a single local patch, the consolidated points, they're displayed in yellow next to the input points in blue, and it overfits to this input, right? But on the other hand, if we train a network on global subsets, the shared weights exploit the redundancy in the single shape, and this encourages a more plausible solution. So here's a couple of results of consolidated point sets generated from noisy inputs, where again, the input is just the single given point cloud, and we generate outlier-free point sets, consolidated point sets, with points on sharp edges. And here's an example of of some results of that in sparsely sampled regions. So we remove those noise and outliers, especially up top here, and fill in points in the sparsely sampled regions. So I want to give like a really big thanks to my PhD advisors, Danny and Raja, and all of my wonderful co-authors, because of course, without them, none of these works would be possible. And thank you everyone for listening. And please check out the links to the code and papers that I talked about here on my website. Feel free to email me, and if you don't get a chance to ask a question now.
Okay, thank you, Rana, and thank you, Lior, for the great talks. And also, thank you for posting so many questions on the YouTube live chat already. And we'll try to go through them all, but sorry in advance for those that we won't get into. And you can feel free to email the authors afterwards if you still have these questions. So first, I have a question for Lior. So one person asked, so IDR seems to train down mostly on like the 2D view of a 3D shape, and they wonder that whether this framework will have some trouble if the shape is not a visual whole. For example, it contains some interesting feature in the interior part of the shape.
Okay, so it's true that we have this masked object, and it helps our model to train better and gain this kind of total shape, the visual hull of the shape. But there are many, as you saw from my results, many high resolution and details. For example, the eyeballs in the skull, it's something that you don't get from the visual hull, and you have to get this information from the multi-view RGB values.
Okay, thank you. And next question is for Rana. So a lot of people ask, for your work on Point2 Mesh, well, how does this method guarantee the result mesh to be watertight and avoid self-intersections?
Okay, that's a good question. So it's guaranteed to be watertight because the initial mesh that we start with is watertight, right? So in order for a watertight mesh to become unwatertight, you'd have to, like, I guess, break connectivity, stuff like that. So we're not breaking connectivity, we're keeping the same exact connectivity, and we're just moving vertex displacements. This does not, however, ensure that we're preventing self-intersections, and those definitely can happen. So the way that in practice we deal with those is, like I mentioned, we pass this initial result to the robust watertight manifold surface generation, and that will clean out any self-intersections that arise and create this nice smooth surface that we kind of reset the optimization and puts us in a good place for the next iterations.
Okay, thank you for the question. And next is for Lior. So usually, like if we work on 3D mesh from the rendering point of view, we will encounter something called a shading ambiguity. Basically, a convex and concave part under some certain lightings, they will be shaded the same. So one person asked whether those non-convexities in the shape will cause any trouble in your reconstruction.
Like, for example, if you can see just like not one strike of the shape, and you can maybe have two places where the VN ray meets the surface. Is what I mean? So basically, I didn't really get into this issue, but we optimize our implicit network to be sign distance function. And this enables us to use somewhat similar algorithm for the sphere tracing. And so I think it's like, from what you understand from the rendering, it just like take only the first intersection of the VN ray into account. And I don't think this kind of can be an option, this situation. And I didn't occur something like that. Okay,
thank you for the answer. And the next question is for Rana. So the question is also for the Point2 Mesh. So they ask whether this reconstruction method, is there any case where this reconstruction method didn't converge to a good solution, for example, on shapes that do not have a symmetry, or like the B prior just very good that you can reconstruct almost most of the shapes?
Yeah, so so in the cases of non-genus 0 shapes, we rely on this Poisson reconstruction, right? We take the Poisson reconstruction, we apply coarse resolution octree, but as we showed before, Poisson is not perfect and it can definitely make errors. And so if our initial mesh isn't good, this is problematic for us, right? So this is definitely a direction for future work. I'll say that the method, like, it's generally important that the method kind of starts with a roughly uniform sized triangles in the initial mesh. Like, if you can imagine, if you have these long skinny triangles, it's really hard to move the vertices. So we kind of do like a uniform triangulation in the beginning so that the initial mesh is sort of, yeah, flexible. Yeah, I think we didn't test it out so much, but I'm guessing that extremely thin structures will be problematic for this. Like, this is a challenging problem in surface reconstruction in general. So this is probably something where it won't do so well.
Thank you for the detailed answer. And the next question is for Lior. So someone asked whether this IDR can be extended to improve the quality of reconstruction from noisy RGB and depth input. So basically, not only the RGB information are noisy, but also the noisy in the depth information.
Once again, the last sentence you said? You mean, yeah, like...
So whether this IDR method can be used to improve the reconstruction from the noisy RGB and the depth input.
Okay. Yeah, I totally think it can be accurate. Maybe it relates also to several other works that we have from our group that works on, that try to optimize implicit neural representation over point clouds. And you can think about such depth information as a point cloud, because you have like the VN ray, and then you get the kind of a mixed maybe depth. So you have this point cloud, and what do you want to do? That you want your implicit network to be 0 on these points. So if you have also depth information, you just like can impose your network F to be 0 on this point. And I think also in the previous work, DVR, they also incorporate depth information in their loss if they have that. Okay. So that's nice.
Okay, thank you. And the last question is for both of you. So both of the work basically shows amazing results on reconstructing a single object. But we wonder whether your methods could be extended to, could be scaled up to, for example, reconstructing the entire scene. Perhaps Rana could start.
Yes, so it's a good question in general, but specifically in our approach, we don't really have a network that generalizes to anything, right? This is a little bit different than, for example, deep geometric textures and in Lior's work, which they have some generalization component. In Point2 Mesh, really the network weights are just used as this regularization, which can be completely discarded once we obtain this reconstructed mesh. So I'm not really sure how we can kind of leverage sets in this setting, but it's definitely an interesting idea for future work. And like one thing that does come to mind is like using some type of similar shrink wrapping technique to, for example, put the mesh of one shape onto another shape, right? So this could maybe collectively use some information from a set. But yeah, it's a good question.
Thank you. And Lior?
Yeah, I think I mentioned that also in my future direction, that there are a lot of works regarding implicit neural representation that also maybe deep SDF and something like that, that also incorporates such a autoencoder or variational autoencoder, and maybe just like concatenate the latent representations to the shape. And by that, learning such a shape space of multiple shapes. I think it's really nice. And also for large scene, maybe there is somehow to maybe divide this implicit neural representation into voxels, and also done similarly in previous works, and maybe learn some large scene, or just like take a bigger network to do that. But it's definitely interesting idea and direction, and I'm sure that there are people who are working on that really hard right now.
I see. Okay, thank you. Thank you both. And also thank you everyone for coming to this week's colloquium. And let's thank our speaker again. And one important thing to mention is that the poster this week is designed by Josh Holinity, and who's a grad student at University of Toronto. And let's thank him for making such a great poster. And for next week, we will be discussing a recent development on developable surfaces presented by Professor Olga Sokin-Hornen and Sylvia Silan. And see you all next week.